let's try to understand a little bit more about asymptotes and where their equations come from. So I have three problems here, three rational equations, and I'm asking to find the horizontal or oblique asymptotes. So let's start off with the first question here. X minus 2 over x squared plus 3x minus 5. Where is the asymptote going to be, the end behavior going to be? We know that the degree of the denominator has a degree of 2, and the degree of the numerator only has a degree of 1. So what's going to happen as we approach infinity, as x approaches a very large number? Well, the bottom part, because it has a higher degree, is going to get bigger much faster than the top part. So essentially we're going to have a smaller number over a very, very large number. And whenever we have that, we're basically approaching 0. So we know that for this equation, we should have a horizontal asymptote at y equals 0. No surprise there. Let's go to the second question. Well, here we have another rational function, and it has a degree 1 over a degree 1. Where is the asymptote going to be here, the horizontal asymptote or slant asymptote? Well, you could do it in a few different ways. We tried factoring out the highest exponent out of the top and the bottom. That way works. You can divide each term in the top and the bottom by the term with the highest exponent. You could do that. And if you do that, you should find out, essentially we have the top and the bottom coefficients, the leading coefficients, tells us that we're going to have a horizontal asymptote at y equals negative 3, right? It's just 3 over negative 1, which is going to give us negative 3. Okay, so no surprises there. Let's go to the third one. This one. How are we going to determine where the end behavior goes for this one? Well, we know the degree of the numerator is a 2, and the degree of the denominator is 1. So in order to find it, we can basically assume or predict that there's going to be a slant asymptote here, right? Because the numerator is higher degree than the denominator. So it's going to basically, the numerator is going to pull that horizontal asymptote up or down, right? To make a diagonal asymptote or an oblique asymptote. And the way we find the equation of that asymptote is we divide the function. So we could do 2x plus 6. Oh, well, actually, we're going to do x squared plus 2x minus 8 divided by 2x plus 6, right? And that looks like this, plus 2x minus 8. So let's do this division super quick. First of all, we're looking for a number that we can multiply 2x by to get x squared. And the answer to that is 1/2 x, right? We would need to divide that 2 by 2. And then let's multiply that back in. So if we do that, we're going to get x squared plus 3x. And then we subtract, we're going to get negative x minus 8. We can ask ourselves, now what multiplies by this to get negative x? And the answer is, again, we would need to get rid of that 2, so it's going to be negative 1/2. Multiply it back out, you're going to get negative x, and then negative 1/2 times 6 is going to be negative 3. So when we subtract those two things, what we're going to get is we're going to get negative 8 minus 3 gives us sounds like negative 8 plus 3, which is negative 5. And that is our remainder. So we've talked about the fact that this here, the quotient of our division statement, ends up being the equation of the asymptote. So just to write down our answer here, I'm going to say that we're going to have an oblique asymptote at y equals 1/2 x minus 1/2. But the question here is why? Why is that true? Why is it true that this is our oblique asymptote and this remainder doesn't actually matter? That's what we're going to get at here. So the way I like to do it, let's take a step back first and look at what happens with normal division. Division of just numbers. Forget about polynomials for a second. So let's say our problem is 23 divided by 5. And that's what we're trying to do. What does that give us? think back to when you did this in elementary school. 23 divided by 5, it goes in 4 times, right? And then how many remainder is there going to be? There's going to be, that takes us to 20, so there's going to be 3 remainder, right? So it's going to be plus 3 remainder, basically. Now, often we don't write it out like this anymore. We don't use remainders when we do division because we have things like decimals and fractions, right? So in order to turn that into a decimal or a fraction, remember this is like saying we have 4 full things plus 3 left over out of 5, right? So it's like saying we have 4 left over plus 3/5 left over, right? The answer to this, if you just do 23 divided by 5 in your calculator, should give you 4.6, right? And the 0.6 is that 3/5. So basically these two statements are equivalent. 23 over 5 is equivalent to 4 plus 3/5. And that's just my way of remembering what the division statement is. So let's write out this division statement because that's going to help us in a second. So we call this the dividend over our divisor is equal to our quotient, which is our answer, plus the remainder over our divisor as well. Oh, can't fit it. Need to zoom out a little more. Remainder over our divisor. Right? That is our division statement. So I'm going to ask you this. Can we rewrite this equation up here in this same form? And the answer is, of course we can, right? So basically our statement becomes, if I want to write it in that way, x squared plus 2x minus 8 over 2x plus 6. That's going to equal the quotient. And the quotient we calculate is 1/2 x minus 1/2. Plus the remainder over the divisor. And the remainder was -5. And our divisor was 2x plus 6. So again, this and this are equivalent to each other, right? They just look different, but they are actually equivalent to each other. So let's zoom in there, just looking at this. So my question for you is, when we're trying to find the asymptote, what are we looking for in the function? Well, we're looking for what happens when x goes to infinity, right? Or negative infinity, right? What happens when x goes to infinity or negative infinity? Well, what I want you to do is I want you to think about what happens to this expression when x goes to infinity or negative infinity. What is this thing going to approach? And we're actually going to break it up into chunks. So when x goes to infinity or negative infinity, I'm going to rewrite this statement out. 1/2 x minus 1/2 plus -5 over 2x plus 6. Let's think about the term on the right first. What is going to happen to this as x goes to infinity or negative infinity? Well, what we're going to have is we're going to have -5, that's never going to change, right? Over 2x plus 6, and the x is going to be a very large number, so like a billion, right? If you plugged in a billion there, what would this evaluate to? Basically, you have a small number over a very large number, so it's going to be very close to 0. It's going to be like 0.0000000 something, right? And same thing happens if you plug in a large negative number, like negative a billion or something like that. So when this thing goes to infinity, or negative infinity, that term goes to 0. And what are we left with? Well, we're left with the divisor, right? So what this tells us is when x approaches infinity or negative infinity, the remainder part of our expression doesn't really matter. It basically goes to 0 because the denominator is going to dominate, right? So we end up with just our divisor. So that tells us when the function is really big, essentially the equation of our function is this, 1/2 x minus 1/2, which that's exactly what we want. That's the equation of the asymptote, right? This slant asymptote that we're going to have. So that agrees with what we found over here, right? That our asymptote should be this. But that's the reason why. It's because this last term, the remainder over the divisor, is going to go to 0. So my question for you now is this. if we go back to those two previous questions, right? The two functions that we found the asymptotes for already. Should this work for these two questions as well? Like, we know pretty quickly what the horizontal asymptote of these two functions are going to be, but could we use the same method? And that's what we're going to investigate here. So I'm going to start off with the middle one. We're going to work backwards now. So I'm going to start off with the middle one down here. So if we go here, again, our process is, it's a rational function. So it's like 3x minus 5 is being divided by negative x plus 3. So let's just divide those two things, right? So essentially we're going to do 3x minus 5 is being divided by negative x plus 3, right? So the first thing we ask, what times negative x gives us 3x? And the answer is going to be negative 3, right? And then I multiply that out. That gives us 3x minus 9. And I can subtract. So negative 5 plus 9 is going to give us 4, a remainder of 4. So again, if we think about our division statement tells us it's 3x minus 5 over negative x plus 3 is going to equal our quotient, which is negative 3, plus our remainder, which is 4, over our quotient, or our divisor, sorry, negative x plus 3. So again, these two things are equivalent to each other, right? It's just a different form of writing it. So let's think about the same thing we did last time. As x goes to infinity, or negative infinity, what's going to happen to this expression? Well, just to copy it out again, we have negative 3 plus 4 over negative x plus 3. And look what happens again to this remainder term on the right. X is going to get very large if we plug in a very large number, right? Which means this expression is essentially going to go to 0. It's going to disappear. What are we left with as x approaches infinity? Well, the answer is we're left with negative 3. What did we think our horizontal asymptote was going to be? You go back to what we originally found. That's exactly the same thing as we found before, right? So this is just another way to calculate where the horizontal asymptote is. Does it also work for our first case, though, where we had this, x minus 2 over x squared plus 3x minus 5? Can we divide these things? Well, let's try it. So we're going to divide x minus 2, right? We're going to divide that by x squared plus 3x minus 5. The question is, can we divide these things? We need something that multiplies by x squared to give us x. Is there anything that does that? And the answer is no, not really. I mean, we could think outside the box and use negative exponents and stuff like that, but that won't really help us here. That will actually give us the right answer, but it makes it way more complicated than it needs to be. Because if we look at a numerical example before we do this, if we were asked to divide, for example, 5 by 23, thinking back to elementary school, what would the answer be to this question? Well, how many times does 5 go into 23? Or sorry, how many times does 23 go into 5? It doesn't go in at all, right? 0 times. And then what's our remainder? The remainder is just going to be 5, right? Because it goes in 0 times, and then there's going to be the 5 left over. Oops, plus 5 remainder. So that's sort of like the same thing that happens with this case here, right? We have, how many times does x squared go into x? 0 times. And then if we multiply out 0 times that term, we're just going to end up with 0, right? 0 times this is 0, 0 times this is 0, 0. We just end up with 0. So then we can subtract to find out what the remainder is going to be, but it's pretty obvious. The remainder is just going to be x minus 2, just like over here, where the remainder was just 5, right? So anyways, this tells us the quotient of our answer is 0, right? So if we write this out as a division statement, it would be x minus 2 over x squared plus 3x minus 5 equals, well, it's the quotient, which is 0, plus the remainder, which is x minus 2, over the dividend. And the dividend is x squared, oh, sorry, the divisor, I meant to say, x squared plus 3x minus 5, right? And we ask ourselves the same question. When we're looking for an end behavior or an asymptote, a horizontal or slant asymptote, we look for where as x goes to infinity or negative infinity. And we can ask ourselves again, what happens to this thing on the right? So just to write it out again, 0 plus x minus 2 over x squared plus 3x minus 5. Well, if you think about it, this thing on the right-hand side, the remainder term, the denominator has a higher degree, right? So it's just like the previous question. It basically didn't simplify anything. If you look, actually, it's just the same thing as this, right? But what's going to happen is the denominator is going to go much, much bigger because it's got an x squared, right? So if we plugged in a large number for x, we get a large number in the top, but we get a much, much bigger number in the bottom because we're squaring that big number. So essentially, this thing goes to 0. So what are we left with as x goes to infinity or negative infinity? Just 0. So that tells us that our horizontal asymptote needs to be at 0, which is what we originally predicted. So the moral of the story here, if we take a step back and look at all these problems, is that there is another way to look at asymptotes, and this way horizontal or oblique asymptotes, and it is to divide the numerator and the denominator. It'll always work, it'll always give you the answer. You just have to remember to write out the division statement as quotient plus remainder over divisor, and then look at what happens when x goes to infinity or negative infinity. My last question for you is, will this ever not work, right? Will the remainder over the divisor never, ever not go to 0? So we saw it went to 0 here, it went to 0 here, it went to 0 here. And think about it. Does it make sense that the remainder would ever be larger than the divisor? And again, going back to our numerical example, right? So I'm going to go back over here to where we did this numerical example. Does it ever make sense that our remainder is going to be bigger than our divisor? And the answer is no, because if the remainder was bigger than 5, right, we would just be able to add another one to this, right, because it went into 23 another whole time. So essentially the answer is no. It will always, always go to 0, right? This last remainder term will always, always go to 0 because the remainder always has to be smaller than the divisor. There you go. Hopefully that clarifies why this works to find oblique asymptotes, and you can see it applies to horizontal asymptotes as well.